We go. I am Mr. Bishop, the guy looking confused in the Bitmoji right there. This is day 2 of chapter 3 in our finite curriculum. We're talking about linear programming problems. So what the heck is a linear programming problem? No, it doesn't have anything to do with computer programming at this point. For our purposes, really it just boils down to real-world problems that have some sort of objective, right? So if you're a business, maybe your objective is to get maximum profit or minimize your costs. So real-world problems that have some sort of objective, we'll call it an objective function. And it's our goal to use a little bit of math to either maximize that objective function or, you guessed it, minimize the objective function. So we're dealing with real-world scenarios, and real-world scenarios have a finite amount of resources. That's a good use of the course title right there. They don't have infinite resources. They have a very finite amount of resources. So what do we mean by that in real-world scenarios in terms of their resources? Well, for example, if you're a company, we could talk about your employees, the materials you have. Maybe you're in manufacturing. The time in a day, the time your employees spend, your capital, right, the amount of money you can spend, the space, are you limited by the space in your building, how much equipment you have, etc. So there's all sorts of things that could restrict us in terms of our resources because they are finite in nature. So when we address these issues of having finite resources for these real-world problems, we're going to model these mathematically, right? We call these constraints. We are constrained, right, by our limited amount of resources, whatever they may be. So we will model these constraints with a system of linear inequalities. Maybe we'll have one inequality for employees, one inequality for materials, one inequality for time. We'll just have a system, right? That just means multiple linear inequalities to model these scenarios. So let's dive into the first question here on the worksheet, the one about packaging. It says, Joe's Confectionery puts together 2 prepackaged assortments to be given to trick-or-treaters on Halloween. Oh, that's nice. Assortment A contains 2 candy bars and 2 suckers and yields a profit of 40 cents. So that's probably important information. 2 candy bars and 2 suckers for assortment A. Assortment B contains 1 candy bar and 2 suckers and yields a profit of 30 cents. The store has available 500 candy bars and 600 suckers. That's going to be important too, I'd imagine. Okay, so before we go to fill in and complete this chart here, let's talk about a couple things. Students ask me, well, why don't they just sell assortment A the most? Because assortment A makes the most money, 40 cents. Well, notice that you have to have 2 candy bars and 2 suckers in assortment A. Where assortment B, you only have to sell 1 candy bar and 2 suckers. And remember, we have a finite amount of resources here, right? We only have so many candy bars. In fact, there's more suckers in our supply for this company. So what happens is there turns out to be a nice balance somewhere between how many assortment A's you should sell and then how many of the assortment B candies you should sell. That will maximize the profit for Joe's Confectionery here. Okay, so I'm going to try to keep the color code going here. Candy bars for A, that was 2 candy bars for A. And suckers for A was 2. And then for B, it was just 1 candy bar and 2 suckers. Okay, that's pretty easy so far. And then this column for available, well, let's talk about availability for a second. That is really our constraints, right? This helps us define our constraints. We are constrained by, in this case, how many candy bars and how many suckers we have at the business. So these are our constraints when we talk about availability. So the candy bars available is 500. Suckers that we have available at the business is 600. And then it looks like all we have left to address is our profit. And this is really going to be our objective function here. The objective for this business, we're trying to maximize their profit. So for A here, for every A assortment sold, it was 40 cents profit. So I'm going to put 0.40. And for B, it was 30 cents, right? Yeah, here we go. 30 cents for B for the profit. I know I've got this thing all marked up in different colors. All right, so we've got the table complete. We've got our objective function or our profit function down here at the bottom. We know we are constrained by the number of candy bars at the confectionery, and the same thing, we're constrained by the number of suckers. So let's take a look at part B. It says, let X be the number of A assortments and Y be the number of B assortments. Referring to the chart, which we just made above, right, our little table, give the two inequalities that X and Y must satisfy because of the availability of each confection. In other words, the availability of candy bars and the availability of suckers. Okay, so since assortment A is going to be X, right, I'm going to put some X's down here. So this will be 2X, 2X, and 0.4X. And then for assortment B, that one's going to be Y. So 1Y for candy bars, 2Y for suckers, and then 30 cents for every assortment B that you sell. So I'm going to put Y's for that. Now, I didn't have to do that in a table, but it seems to just make things easier when we go to write these inequalities at the bottom. So let's start with candy bars. All right, let's write this constraint for candy bars. We know we've got 2X from assortment A plus 1Y, right, because there's 2 candy bars in assortment A and 1 candy bar in assortment B. But no matter how many we sell from assortment A and assortment B, no matter how many we sell, we can't go over a certain number. And that number is 500. So my question for you is, what sign is going to go there? We know this is an inequality, right? We're supposed to be making inequalities. Well, if we know all of the assortment A and B can't go over 500, I mean, you could certainly sell less than 500, but you can't go over 500, then we need to make this a less than or equal to. Remember, we are limited by our resources in this case. So the candy bars, no matter how many assortment A or assortment B that you sell, you've got to stay at or below the total amount, which is 500. All right, and let's go ahead and write the inequality for the suckers. We've got 2 suckers for each of the A assortment plus 2 suckers for each of the B assortment, so it's 2X plus 2Y. And the total number of suckers is 600. So again, we can't go over 600. We could certainly sell less than that, but we are limited by our resources here. So again, we need a less than or equal to sign here. All right, so there we go. We've got our 2 inequalities that describe those constraints, right? We're constrained by the candy bars and suckers in this case. Part C says, give the inequalities that X and Y must satisfy because X and Y cannot be negative. Remember, X was like the number of A assortments that were sold, and B was the number of, or Y was the number of B assortments that were sold. So we can't have negative candy assortments, so we know that you have to sell at least 0, meaning x has got to be greater than or equal to 0, and y has got to be greater than or equal to 0. And since we're dealing with real-world problems, this is always the case, right? You have to be greater than or equal to 0 in terms of the number of items. Last but not least, we are asked to express the earnings or the profit, our objective function, from producing X packages of assortment A and Y packages of assortment B. So that's already expressed for us here in the bottom. Why don't we use P for profit? So P equals 40 cents for every X plus 30 cents for every Y. There we go. It's already in the table for us. We're just going to say that is what P equals for our profit. That's our objective function here. All right, I want to help you set up the next question just a bit, and then that will be all for this video. It says, a truck traveling from New York to Baltimore is to be loaded with 2 types of cargo. Each crate of cargo A is 4 cubic feet in volume, weighs 100 pounds, and earns $13 for the driver. Each crate of cargo B is 3 cubic feet in volume, weighs 200 pounds, and earns $9 for the driver. The truck can carry no more than 300 cubic feet of crates and no more than 10,000 pounds. Also, the number of crates of cargo B must be less than or equal to twice the number of crates of cargo A. Part A says we're going to begin by just filling in the chart, basically taking this word problem and converting it to the numeric values here. So we've got volume and weight to worry about, and we have cargo A and cargo B. So for cargo A, it said 4 cubic feet of volume, and it weighs 100 pounds. Earns $13 for the driver, so earnings is $13. And for B, it was 3 cubic feet in volume, 200 pounds, and $9 for the driver, so $9 here. But this is a real-world problem, right? We can't just ship unlimited cargo. So we are limited by our space and capacity. It says the truck can carry no more than 300 cubic feet of crates. So for the capacity here, that's volume, right? 300 cubic feet fills up the truck with volume. So I'm going to put 300, that's our capacity. And then our weight max is 10,000 pounds. So 10,000 pounds. All right, so our chart is ready to go here. We need to start by coming up with those inequalities based on the volume and the weight, right? So we're limited by the volume the truck can carry and the weight. And it says X is going to represent the number of crates for cargo A, right? So basically I'm going to put X's through this way. And then Y is going to represent the crates for cargo B. So Y's will go for cargo B crates. So let's start with the volume here. So for the volume, we have 4x plus 3y, and then 300 is the max. So just like the last problem here, we can go below 300 in capacity, but we can't go above it. So the inequality sign we need here is less than or equal to. All right, and then for the weight, let's see, we've got 100 from cargo A, so 100x plus 300 from, oh, there's a mistake right there. That should be a 300, huh? I said it, but I didn't write it the first time. There we go. 300 from cargo B, and our capacity, our max capacity, is 10,000. So since we can't go over that number, it has to be at or below 10,000. So I should see a less than or equal to sign there. Okay, and then for part C, it says, give the inequalities that X and Y must satisfy because of the last sentence of the problem, and also because X and Y cannot be negative. So let's take care of that one in blue first. We know that one already. We've already done it today. We know X and Y cannot be negative means they have to be at least 0. So let's knock those out. There we go. But in red here, what is meant by because of the last sentence of the problem? The last sentence of the problem says the number of crates of cargo B must be less than or equal to twice the number of crates of cargo A. Okay, we need to put this in terms of X and Y though. So we know the number of crates of A, we called that X, right? And the number of crates for B, we called that Y. So this says the number of crates of cargo B, that's Y, I'm going to go ahead and write a Y down here, must be less than or equal to, I can handle that too, don't worry, I got that sign, twice the number of crates of cargo A. So I'm going to put 2x because that's what cargo 8 crates were represented by. So there we go. That handles the last sentence of the problem. Okay, I'm going to leave you to finish this problem and the last problem on the worksheet. Just as a little reminder, refresher, I'm going to take us back to the opening here. So we've approached a few real-world problems. We talked about the objective functions and whether we'd like to maximize the profit in these examples. We talked about constraints and having finite resources in the real world. So, my dog Brooklyn did not like that last comment, so I better end this video. Thank you for watching.